Thanks to the organizers for inviting me. This has been great. Wonderful workshop. The setting is beautiful. Here are some of my favorite places. All right, so let me tell you the kind of general idea of the talk quickly. So we're considering several types of structured matrices, and I'm considering very particular types of structured matrices. Unit norm type frames, normal matrices, weighted adjacency matrices of balanced digraphs, which seem kind of like a random selection. So there is a unifying theme here. And so the main idea of the talk is that these all have some interpretation through the lens of symplectic geometry. So this whole project, which is all joint work with Clayton Schonkweiler, by the way, the idea is to prove theorems about matrix spaces that people in like signal processing would care about. So they're very applications-oriented theorems, but the proofs all use tools from symplectic geometry. So I'll come back and explain what these spaces really are later. So I was going to start with an overview of some concepts from symplectic geometry. Luckily, for the sake of time, Peter gave a very well. I'm gonna make you go back and look at his slides, but I will just for the sake of people who don't think about symplectic stuff, give you a super intuitive picture of what this stuff is, just so you can have something to grab onto throughout the talk. So symplectic manifold is a manifold with some geometric structure, and locally it looks like a complex vector space with the negative imaginary part of a Hermitian inner product. Okay, so an example to keep in mind is the two-sphere. So the geometric structure changes from point to point. It eats a pair of tangent vectors, gives you a number. So this particular symplectic structure eats the two tangent vectors, returns the signed area of their parallelogram. Okay. And one of the main kind of tools that we're using is the notion of a momentum map. Okay, so this comes from a group action on the symplectic manifold, and the definition is, fairly technical, but the idea is that it's a function from the manifold to the dual of the Lie algebra, which somehow encodes like the conserved quantities of the group action. And that intuitive idea is probably enough to get through the talk. And so in red, I say isomorphic to G. So I'm kind of abusing notation, kind of always thinking of G star as being the same as G through some choice of inner product. And as an example here, if I take my two-sphere symplectic manifold, I can rotate it around the z-axis. That's an S1 action, okay? That has a momentum map, and it's given by height along the z-axis, where I'm, once again, abusing notation and thinking of the dual of the Lie algebra of S1 as the z-axis. Okay, and then the point is, so these things exist sometimes for certain group actions, and they have all sorts of amazing properties, and it's this highly structured sort of thing, and we'll exploit that structure. Okay, so most of the talk is about these spaces of frames, which is, I would imagine, unfamiliar to people here. This is coming from a very applied perspective. So these are things that people in signal processing care about, or harmonic analysis. Let me say what the space is and then explain like why people would care about this, because it maybe looks a little bit random if you haven't seen this before. So an n frame in complex d-dimensional space is just a full rank matrix. The reason for the extra terminology calling it a frame is you can think about frames in Hilbert spaces, infinite dimensional Hilbert spaces, in which case there are more conditions to the definition. But in finite dimensions, it's just full rank. Okay, so then people in signal processing care about frames with special properties. And some special properties they care about are unit norm and tightness. So unit norm is kind of obvious. The columns of the matrix are all unit vectors, okay? Tight is a little less obvious, and this is saying that FF star is a multiple of the identity. Okay, so let me give you some context. Why should people care about this? So like I said, this comes from signal processing, so I think of CD as my signal space, okay? And so I'm thinking of n as being, of course it has to be at least d, but I'm thinking of n as typically being a lot bigger than d. That's why n is capitalized and d is not. And so the idea is you take a signal in your signal space and you take measurements of this signal. And mathematically this is modeled by taking inner products. Okay? So the frame is giving me some big collection of measurements of my signal. All right, so it's sending me from my lower dimensional signal space into this higher dimensional representation space. Okay? The question that always is asked, and I think rightly so, is like, okay, why is n so much bigger than d? Why don't you just use a basis to represent your signal, of course? But the point is this is coming from applied math where everything's noisy, okay? So imagine you take the measurements of your signal and then you send them to somebody else and they want to reconstruct the signal from those measurements. In the transmission process, you can lose measurements, right? And if you only took d measurements and you lose one, then you're screwed, right? So you can't reconstruct the signal on the receiving end. Also, measurements are noisy, okay? So taking these redundant extra measurements kind of averages out the noise, basically. So that's why people use frames. So we have this process, which is take a signal in CD, send it to a measurement in C big N, okay, redundant measurements. Then I reconstruct by applying F. I end back up in CD. So the tightness is saying that this thing that people call the frame operator, FF star, is a multiple of the identity. So the chain of going from signal to reconstructed signal, if you're tight, is just a scaling. The multiple? So yeah, so that's a good question. So in general, tightness is just saying a multiple of the identity. If I also impose unit normness, then it has to be that multiple. And you can figure out why that's the case. Okay, so I was saying something about noise that can be pinned down as a theorem. And so this is like some sort of an amalgamation of a bunch of theorems that are classical in this field. So among all n frames, the unit norm tight ones are kind of best in terms of reconstruction error. Okay, so that's why in particular I like these type of frames. Okay, so now that I've convinced you why you should all care about the space of frames, it's very useful from a signal processing perspective, you can start to ask geometric questions about this space, okay? So this space is not necessarily a manifold. It can be singular, and it can potentially have weird topology. And to kind of illustrate how poorly that was understood, there was this old conjecture which asks kind of the most basic topological question, is this space connected? Okay, so this came to be known as the frame homotopy conjecture, going back to 2002 from Larson, who conjectured the answer is yes, and that remained open for 15 years, and there were several papers proving special cases of this, and was eventually proved by Cahill, Mixon, and Strawn in 2017. Their proof is constructive and quite technical, and it's unclear how you would generalize this to other spaces of frames because it's so specific and explicit. So the first result that we had kind of in this direction of using symplectic geometry in signal processing was to generalize this to these more general frame spaces. Okay, so you can, instead of unit norm tight frames, you can say, okay, what if I prescribe other norms for my vectors? What if I prescribe a different frame operator? Okay, so I pick some R1 through Rn's, or I pick some positive definite Hermitian matrix. The point being, people care about this because, okay, so the vector norms is saying like this is kind of the power of a certain measurement, okay, and you might, in general, equal power makes sense, that's like unit norm, but you know, there could be certain data-driven circumstances where you don't want them all to be the same power. Changing the frame operator, people say that, okay, so unit norm tight frames are best for white noise, okay, but if you have colored noise, then you're supposed to tune the frame operator to the covariance of the noise model. So, yeah, and so then our result is that, yeah, in fact, the frame homotopy conjecture works for these general spaces of frames, but the point is, instead of doing this constructively and very explicitly in all possible cases, we just use these symplectic principles, and it ends up becoming like a 3-line proof, actually. So here's the idea. So I'm going to consider this space, which is not the frame space, so this is some related space. I look at spaces of matrices such that the frame operator has prescribed spectrum, okay? And then I mod out by the action of UD by left multiplication. So I get some sort of moduli space of matrices. This is a symplectic manifold in a natural way, okay? And in fact, this is a complex flag manifold, essentially, okay? If the lambdas are all 1, or maybe if all the lambdas are 1, then this becomes a complex Grassmannian. So these have like more or less canonical symplectic structures. Okay, so then I look at this space, which is a symplectic manifold, and this has a torus action, U1 to the n. So U1 is a circle, to the n makes it a torus. I'm really thinking of that as n by n diagonal matrices whose diagonal entries have unit magnitude. Okay, these are complex matrices, of course. So that's Hamiltonian. Hamiltonian just means like a momentum map exists, essentially. So the momentum map, in this case, takes my UD orbit of a matrix and sends it to this collection of column norms squared. Which, so just from this very intuitive perspective, that's like a conserved quantity of this right multiplication action. All right, so then here's kind of like the punchline of this whole perspective on these sorts of problems. Once you recast these kind of matrix theory problems in symplectic language, then you have access to all these powerful theorems proved by famous people that are very useful. So then we can apply this theorem of Atiyah. So this is a very famous theorem of Atiyah, which says that level sets of momentum maps of torus actions are always connected. Okay? And so the point is we're trying to prove something about connectivity, so then we're essentially done, okay? So I can take this momentum map, look at this level set, okay, where the RJs are coming from my prescribed norms. That level set is not exactly the frame space, but it's close enough that you can kind of get the result you want with elementary arguments from there. Okay, so the point is the symplectic perspective lets you hit things with a big hammer that just allow you to apply this machinery that's been developed over many decades. Okay, so we prove in follow-up papers, we prove other things addressing kind of open questions in the literature about these spaces. So there was an open question, when are these frame spaces manifolds? As I said, they could be singular. And we characterize this. So here we're not prescribing the frame operator exactly, we're prescribing its spectrum. This is a little bit more natural from a symplectic geometry perspective. But so given a prescribed spectrum and a prescribed set of column norms, this is a smooth manifold if and only if, like, technical condition. Okay, and you don't have to pay too much attention to exactly what this condition says, but just to run through it quickly. So it depends on these parameters, R and lambda. And what can go wrong if I can partition R and partition lambda in such a way that the partition blocks majorize each other, is what people say, then that's when I get singularities. So majorization is this kind of weird, all the cumulative sums have to have this bound. Okay, so that maybe looks like a weird condition. If you know the Schur-Horn theorem, that's not such a weird condition, possibly, but we don't have to dwell on this too much. Okay, so we can say exactly when these are manifolds, and we can say exactly what the singularities look like in the case that they are singular. Okay, so if they're singular, meaning you have this kind of partitioning and this majorization property, then the singularities occur exactly at what are called orthodecomposable frames. So that's the case that I can take my ambient CD, decompose it into orthogonal subspaces, and my kind of the frame lives as two separate frames in each of those pieces. Okay. And you could say, like, geometrically, what do the singularities look like? They look like products of quadratic cones and manifolds. And that's really coming from symplectic geometry theory, so this result of Arms, Marsden, and Moncrieff. And okay, so I'll mention this in a kind of simple setting, the unit norm type frame setting. This was known basically, this condition reduces to D and N being relatively prime. Let's see, and let me give one more example in this frame setting. So this is more of like a random matrix theory type result or compressed sensing type result. So extremely roughly, what is compressed sensing? It says that if I pick a random kind of short fat matrix, so N is bigger than D once again, so I pick a random matrix, this will be good at compressing sparse vectors. What does that really mean? So I'm taking, now I'm thinking of the map V goes to FV, so that's going from high dimensions to low dimensions, okay? So good compression means that I can invert that map, right? Which of course I can't do in general, but if I'm looking at subspaces of vectors that have a lot of zeros, then this becomes more feasible. So the real theorems in compressed sensing say, give quantitative bounds on how likely you are to be good at compressing. So the question we were thinking about is, can you improve the quantitative version of the compressed sensing theorems if instead of choosing a general random matrix, I choose a random frame, or random unit norm type frame, okay? And so there was evidence in the literature to suggest that the answer is yes, so people have studied this empirically, but there are no proofs. We don't prove this, we prove a very baby version of this, okay? I won't go into details, but you can think about why this would be kind of a necessary condition for things to work correctly. So kind of a first step is to say, what is the probability that a random unit norm type frame is full spark? Full spark means I take my matrix, so it's D by N, I can choose D columns, and I say, is that spanning, okay? So in general, I just need this matrix to be spanning. It's full spark if actually like all the feasible subsets are also spanning. So knowing that that happens with high probability is necessary for any sort of compressed sensing type result to work. Okay, and so we answer this question. So we once again work in these not just unit norm type frames, but these kind of generalized frame spaces. And we show that one of three things happens. Okay, so this space can be empty, which I glossed over before, but if you choose weird norms and weird eigenvalues, then this can just be empty. Like you can't have frames with certain data. Or it could then be non-empty, and it can be non-empty and contain only frames which are not full spark. So all of the frames in the space are degenerate in that certain sense. Or if it has full spark frames, then like everything's a full spark frame. Okay, so it can be non-empty, and full spark frames are they're full Hausdorff measure in the frame space. So this proof is a little more complicated. So I'll just tell you kind of like the ideas that come up in this proof, and it's once again symplectic ideas. So we consider this generalized frame space, then we mod out by certain group actions. So that turns this into a symplectic manifold, or really it's a symplectic stratified space, if I'm being honest. Okay, but it's a thing that we can work with. And this has a Hamiltonian torus action. I won't tell you what the torus action is because it's not as simple as the ones that we've seen so far, but I'll tell you what the momentum map is. So the thing that's conserved by this certain torus action are these eigenvalues of these partial frame operators, okay? So I take the first j columns of my matrix and compute these products, these kind of projectors, FL, FL star, add those together, I get these kind of low rank approximations of the frame operator, and I can sort the eigenvalues, and these are the things that pop out of the momentum map. Okay, so these eigenvalues satisfy a certain pattern, and if you're a symplectic person, then this maybe looks familiar. So this is what's called a Gelfand-Setlin pattern. So this all kind of corresponds to what's called the Gelfand-Setlin system, some integrable system. So the eigenvalues are interlaced in this particular way. Okay, so I'm not showing any of the zero eigenvalues. These are the partial frame operators are all low rank, so there's a lot of zero eigenvalues. So the potential non-zero ones have to satisfy these inequalities. So you get kind of coordinates for the symplectic manifold in a certain sense. and these coordinates carve out a convex polytope. Okay, and this is a general kind of symplectic geometry principle. Moreover, I can reason about measure theoretic properties of the frame space using the Lebesgue measure on this polytope. So there's some correspondence between these measures. So the theorem is basically proved by sending everything to this polytope and working there. Okay, and that's, once again, this kind of big symplectic idea, so this thing called the Duistermaat-Heckman theorem. Okay, so now I'm on to other applications. What is my time looking like? 15 minutes. Perfect. I need 10, so we're good. All right, so let me talk about some other applications. And once again, so at the beginning I showed you like some spaces of matrices. It looked like some kind of random assortment. But the point is these same types of geometric ideas apply to these other matrix spaces. Okay, so yeah, so I mentioned normal matrices. So this is another area where these sort of ideas apply. So a matrix is normal if it commutes with its conjugate transpose. And from a math perspective, these are interesting just because like this is where the spectral theorem works, basically. So these are exactly the unitarily diagonalizable matrices. From an applications perspective, people care about these. So they have particularly nice spectral properties, so that they're like spectra are Lipschitz stable. So people use this in control theory. This is also used in mathematical biology. Because normality somehow governs dynamics on networks. So this all motivates this kind of general problem. So I'm handed an arbitrary square matrix, and I want to say, what's the closest normal matrix to the one I started with? Okay, so this is the nearest normal matrix problem studied pretty classically. A thing that people used, and kind of the obvious thing to consider, is this quantity. So I say, I'm handed an arbitrary d by d matrix. I want to say, how non-normal is it? I think that quantity in blue on the right is a pretty natural measure of this. I say, how big is AA star minus A star A? Or bigness is measured by Frobenius norm. Okay, so then a thing you might try to do to solve this nearest normal matrix problem would be to gradient descend on that energy. Okay, so the zeros of this energy are exactly the normal matrices. You might say try to gradient descend to the zero set. A problem which we'll reconcile almost immediately is that this is not a quasi-convex functional. Okay, so just general convexity, convex optimization doesn't tell you that, that this plan works. Okay, you could potentially get stuck in local minimum. So it's not quasi-convex, whatever. It is the norm squared of a momentum map. Okay, so the map taking A to A star minus A star A is a momentum map for the conjugation action of UD on C d by d. I think I'm underselling this a little bit. So this class of function really has amazing gradient descent properties. Okay, so I think the best reference is Kirwan, but there's also a nice paper of Lehrman on this. But I won't say exactly what these amazing properties are, but this is a very nice class of functions. So if you have a function which arises naturally in this form, you gain a lot. So that's enough to conclude that this plan of gradient descending this energy functional works. Okay, so I'm starting with an arbitrary d by d matrix. The theorem guarantees that if I gradient descend this energy functional, I will end up in a normal matrix. I won't get stuck in a local min. Moreover, it preserves realness. So if I started with a real matrix, then my resulting normal matrix will be real. It preserves eigenvalues. And so these are things which are not preserved by the kind of standard nearest normal matrix algorithms. Okay. We can also get quantitative bounds, so like the distance that you travel basically is bounded by the energy of what you started with. So this is coming from a Woshevich inequality. And you can take this whole story and adapt it to preserve total weight. Okay, so it's feasible that you start with a matrix and then you want to gradient descend it, and you just kind of like really decrease the magnitude of the entries. You can like shoot to zero, for example. You can adapt this whole story to preserve the Frobenius norm of where you started. Okay. And so an application of this is to consider the topology of the space of unit norm normal matrices. So I think that I was claiming that we were proving theorems that were relevant to signal processing people. This one is maybe not so much, but it's a fun application. So the space of normal matrices is a cone, so it's contractible, so there's no topology there. But if I consider the space of unit norm normal matrices, so I'm fixing Frobenius norm 1, these can be real or complex. This can have interesting topology. Okay, so here's a picture. So I'm taking 2x2 matrices with Frobenius norm 1. Okay, so it's a 3-sphere. I'm stereographically projecting to R3. And I'm coloring the unit norm normal matrices in pink in this picture. Okay, so we see that that's not simply connected. The blue rings are the image of the nilpotent unit norm matrices. So those play a role in the story as well, they're in the picture. But the point here is that unit norm normal matrices can have non-trivial topology. But we show that generally the low-dimensional homotopy groups vanish here. Okay, so if k is less than 2d minus 2 in the complex case, then the homotopy groups are trivial. And if k is less than d minus 2 in the real case, then the homotopy groups are trivial. And the proof, the proof itself doesn't use any of these kind of symplectic concepts, but besides the fact that we know, okay, so we use this gradient descent property to show that the space of unit norm normal matrices is homotopy equivalent to non-nilpotent matrices. Okay, and the homotopy equivalence is given by the gradient descent flow. So once you know that, then computing homotopy groups reduces to computing homotopy groups of non-nilpotent d by d matrices. The nilpotent matrices are stratified space, and the strata are high codimension, so then this result follows by transversality arguments. Okay, and quickly, one last application is to balancing directed graphs. So this is back in a very applied setting. So the idea is you have a directed graph, and it's weighted, so that there's capacities on each directed edge. And you would like to reweight the edges in a way that the in degree and the out degree at each node are the same. Okay, so this is like a very practical problem, right? So imagine this is a road network with a bunch of one-way streets, and the edge weights are like traffic flow capacities. I need it to be the case that the number of cars which enters an intersection is equal to the number of cars which can leave that intersection. Okay, otherwise I have problems. So you start with your initial weighted matrix and then try to reweight it so that it's balanced. And so I'll just summarize this and say, like, basically the same sort of concepts allow you to do this reweighting. We're gradient descending, once again, a norm squared of a momentum map. And in this case, it's kind of very similar to the one we had before, but I take the diagonal of this AA star minus A star A. Okay, so then the point is like that functional's not quasi-convex, but because this is from a special class of functions, we can prove that you don't hit a local min. So this will always converge actually to a balanced graph. And it preserves all sorts of things. So it preserves eigenvalues or principal minors. And also we can adapt this to preserve total weight once again. And that's especially relevant in this setting because if I have a certain amount of traffic that has to get around my city, like when I'm balancing, I have to maintain that amount of traffic, is the idea. Okay, so there are lots of open questions, but maybe I'll leave that to the discussion if people want to talk about this. So thanks.
Thank you.
Thanks. So the definition of spark that you had is equivalent to the matroid being uniform.
Okay.
Is there anything you can say about when the matroid is not uniform? So you're just specifying which columns are independent. And so you said you should make all of the columns, sorry, not all, you should make any D column should be independent. And
That's
that gives
right.
the uniform matroid. So what if you specified some other combinatorial collection of columns that should be independent?
Okay. Yeah, I think so. Yeah. Well, okay. So the perspective on this is like this kind of random matrix theory. So that's why this kind of fully connected matroid, is that what you said? The uniform matroid.
Yeah, the uniform.
So
random matrices will, of course, have a uniform matroid.
Yeah. So that's kind of like the right notion from this perspective, and we use that heavily in the proof because we say like, okay, if I want to know that all of these selections have this property, then I can kind of just pretend it's the first set of them that have this property and use randomness for there. So yeah, I think that the answer probably becomes a lot more complicated if you start thinking about specified selections. Yeah. And I guess, okay, and then you could push this further and say, what if I don't need all D columns and certain sets of K columns are full rank, and yeah. So I don't know what happens, but I think it sounds interesting. Yeah.
Thanks.
I don't know who raised their hand first. So. Let's start.
Thank you. And outside the remark and question, so your results about high connectedness that manifold, they resemble the so-called results of Kato Matsumoto on the high connectedness of Milnor fibers of intersection of quadrics. Yeah, I mean, did you compare these results?
No, I didn't know that would be relevant actually. So it's
that's a topic known in singularity theory.
great. Okay, yeah, I'll have to get the reference.
You have kind of a complete intersection, then you take intersection of small sphere, and normally this result is highly connected, and even the numbers which you showed, they resemble.
Okay, interesting. Interesting.
Oh, sorry. Okay. But the main thing is that the speaker has heard me. Yeah? Okay.
Okay, yeah, that's great. I'll have to get that reference. So I guess it's also kind of transversality arguments and stratifications. Okay, I mean that's like the tools we use, but that's sort of the natural tool to use.
It's from singularity theory, let's say.
Okay, great. Thanks.
In compressed sensing, you have this restricted isometry.
Yes.
And the upper and lower bounds seem to be the eigenvalues of the restricted frames. So
Yeah, that
is there anything to
seems
say
like the
with
right
the momentum
guess.
map? And
Say again.
is there anything to say or any connection between the choice of the momentum map and tightness of the bounds for the restricted isometry property?
That's totally the hope. So this is the thing that we proved, this full spark property, is basically like a proof of concept to see if we could try to push more quantitative things in compressed sensing. So the plan is to try to use the geometry of this Gelfand-Setlin polytope and see if we can, if we understood the geometry of that really well, the idea is that maybe we can figure out probabilistic things about restricted isometry property. So if there's anyone who thinks about Gelfand-Setlin polytopes a lot and understands them really well, I think that would be helpful to talk to them.
So my question was about your dichotomy theorem. So I imagine it's testable in that if you give you a candidate, you can check and see and then sort of understand if you're in the situation where there exists. But do you have a criterion that you could apply? Perhaps not necessary and sufficient, but
Yeah, no, so I didn't write the full statement of the theorem actually. So the conditions on R and lambda which tell you which category you're in are explicit, and it's basically like there's this majorization thing I was talking about. Yeah, it's whether you saturate this bound. Okay, so if you have equality in any of these places, then you get this kind of weird middle condition where everything's kind of bad. Okay, so if you don't have these inequalities, you're empty. If you achieve equality and the rest are inequalities, everything's bad. If everything's strictly inequality, then all's good. Yeah.
Do you know any interesting energy functionals on the space of frames where you could make use of the Hamiltonian flow?
Yeah, I mean, so we use that sort of idea. No. But so presumably there's something that exists. It's yeah. I think we're handling these kind of big properties of frames, and I think we need to talk to frame theory people and see, is there something within the space of frames you would like to optimize, or you'd like to understand the dynamics there. But yeah, I couldn't think of one that we've considered actually. But yeah, that's a goal.
So I have a question about the theorem where you compute the homotopy group. So yeah, I haven't.
Yeah.
Do you think that there's any chance one might be able to use similar techniques to prove a quantitative version where you say if I pick a threshold T for a norm, then how small should the norm be of a homotopy between two elements at the first norm? I mean, a persistent version of this.
Yeah, that's interesting. Yeah, I mean, like, the tools we used here were fairly basic, really. It was just, this is all driven just by like codimension. So I think if you really dug into it, like certainly this could be tightened up. The other thing, so I think something that's in this direction that's a little bit more difficult is considering the higher homotopy of these generalized frame spaces. So we proved that they're connected, and I think you really need trickier tools than what we used in that other theorem to talk about higher homotopy here, because you can reduce it via homotopy equivalence to some also a priori simpler space to compute the topology of, but it's not so simple as just like complement of nilpotent matrices. So which is to say, I think there's a lot of room to kind of extend these these techniques. Yeah.
Okay, thank you again. Thank you again.
Thank you.